My name is Markus Fallmann and I'm a PhD candidate at the Institute of Mechanics and Mechatronics at the Vienna University of Technology. In this presentation I'm going to walk you through a very interesting research project of ours that is done in cooperation with the industrial partner Product Blocks and which is funded by the Austrian Research Promotion Agency, FFG for short. The project is called Distributed Model Predictive Control for Modular Cooling Units and aims to reveal how such modular cooling units that work towards a shared aim should be controlled independently to still fulfill global objectives. In this talk I will provide a short overview of given requirements, the system dynamics and the control concept itself. I will finish with a short preview of how such a control scheme can be handled mathematically. But let's start by outlining the basic challenge. If we look at the global movement of goods, trucks are of major importance, especially for the last few miles. In addition to that, some goods do not just need to be transported from A to B, but the temperature must be kept within a certain range. For example, food and pharmaceutical industries face enormous financial losses a year by violating such limits. It is estimated that 700 million tons of food waste a year solely result from insufficient temperature conditions during transport. And besides that, a lot of energy is needed for operating such cooling units. All refrigerated trucks combined emit approximately 13 million tons of carbon dioxide a year and therefore have a very large environmental impact. Our main objective is to keep better track of given temperature limits, to inhibit or at least reduce the amount of wasted goods, and to simultaneously increase overall efficiency. That of course goes along with a smaller environmental footprint. But how can we accomplish such desirable objectives? Of course, by designing and implementing an appropriate control strategy that defines how these modular cooling units should be controlled. In terms of control design, we have to translate and specify those two overarching goals. So let's look into the details. Firstly, the temperature of the goods in the cooling chamber should remain within a certain temperature range, regardless of any disturbances. Secondly, compared to the energy consumption of a standard control approach, here schematically depicted in gray, our algorithm should be more efficient. Furthermore, our control scheme should be able to handle a varying number of cooling units. For example, a truck that operates in the north of Europe may be equipped with 2 cooling units, while a truck that is used in a region close to the equator may need 4. And fulfilling this aspect is also vital for the fail-safe performance of the overall system. In this sense, we are asking for an algorithm that still performs adequately, albeit one or more cooling units exhibit a fault. And to further improve reliability, each cooling unit should be equipped with its own controller. While many state-of-the-art approaches use an additional global controller to ensure an optimal workload distribution, we design a communication strategy instead that allows a completely distributed setup. Furthermore, we should be robust in the face of slight parameter changes. For example, a very likely source of such variations in mobile cooling applications is degradation or also demolition, damage of the insulation. And our control approach should be able to handle that. As in almost every control application, also asymptotic stability is crucial for our application here. The next aspect refers to solutions optimality. Although we are acting on a purely local level, the communication strategy should be able to yield a solution that is at or at least sufficiently close to an optimal one. And finally, our system possesses some special features that we would like to incorporate and explicitly consider in our mathematical description. So let's look into these. The cooling unit, here in the schematic depicted in blue, consists of a classic refrigeration circuit that uses propane as its coolant, and the heat flow queued at ambient is released into the atmosphere. In addition to this fundamentally needed cooling circuit, there is another cycle that uses a mixture of water and glycol as its coolant. That extension improves systems flexibility, as the glycol-water mixture may serve as a cold reservoir. Compared to some standard approaches, not the evaporator, but this heat exchanger, let's call it the air chiller, is located within the cooling chamber. So the heat flow Q at 0 coming from the inner air volume is transmitted to the glycol water mixture at this very point. The question arises, why do we choose such a comparably complex system architecture? What are the possible advantages? On the one hand, the refrigerant propane in our setup cannot contaminate any goods within the cooling chamber, as they are separated by the glycol water circuit in between. On the other hand, the storage effect of the glycol water mixture offers the opportunity towards a more appropriate, more flexible operating strategy that aims to keep track of given temperature restriction and also keep an eye on overall efficiency. So of course, this additional circuit is one of those special features I've been talking about. One question remains, how can we control our cooling unit? The control inputs are the compressor switch, the compressor speed, and the air chiller fan switch in our project setup. So one can easily see now that we have to define continuous as well as binary logical control inputs. Now let's go into the further influences, disturbances acting up in the cooling chamber itself. Of course, ambient air temperature, because no insulation is perfect. Additionally, also weather conditions and especially solar radiation, because solar radiation influences in a significant manner at least the temperature of the insulation close to the outer surface. Furthermore, also the initial temperature of the goods at the time of loading, because this temperature and the thermal capacity disturbs the inner air temperature. But however, door openings have the most significant impact on the inner air temperature. Despite that, most of the current control approaches only cover them heuristically. We, by contrast, incorporate them in an explicit manner and model them as an actual connection between the cooling chamber and the ambient air. This is of course the second special feature of our model and allows us to better cover given circumstances, but of course introduces an additional binary variable, the door opening. And such systems that cover binary and continuous variables, states, control inputs are denoted as hybrid. And to solve a model predictive control scheme for such hybrid systems, a mixed integer programming problem must be solved that is usually computationally expensive. And that's another reason why we prefer several local rather than one global controller in our project setup. Now, coming from one cooling unit, we will have a closer look into a setup with more than one cooling unit. We consider 3 of them acting upon one cooling chamber. The negative sign here indicates that the actual physical heat flow is pointing, of course, in the opposite direction. And each cooling unit is managed by its own controller that defines the control inputs at every time step. To better understand the workload of a single agent, we zoom into one of these controllers and have a closer look. Firstly, measurements. Global and local ones are fed back into the algorithm. Secondly, there is some sort of communication among controllers that allows each controller to know what all the other agents are planning to do in the future. And finally, references and predictions are transmitted to every controller. Those predictions may refer to door openings, to weather forecasts, or to how the ambient temperature will evolve within the horizon. The controller takes a model of the insulated cooling chamber and knowledge about how the cooling unit actually works to minimize an objective function J total. We divide it into J temperature that keeps track of given temperature restrictions and J energy that penalizes the energy consumption. Minimizing J total, subject to model dynamics, temperature and input constraints, yields the optimal solution. And because we have used an optimal or an appropriate communication strategy, we are able to find a solution that is at or at least sufficiently close to an optimal one. After finding such a solution, we can now apply values for the control speed, the fan switch and the compressor switch to our cooling units. By now, we have drawn a very shallow picture of what hybrid model predictive control actually is. So let's dig a bit more into the equations underneath. Under some mild conditions, it is possible to transform a hybrid model description into a series of inequalities, and these inequalities may look like this in a very general form. E are constant matrices, delta and C are binary and continuous auxiliary variables that are inevitably necessary to allow the transformation coming from the hybrid system description and going into a series of inequalities. U of k denotes the control inputs at the current time step k. They are further divided into continuous and logical ones, UC and UL respectively. V of k, these are the model disturbances, and in the final application they may be measured, for example ambient temperature, or predicted assumed, for example when will the door opening happen. And the same partitioning as for the control inputs applies here as well. Now, coming from the model description, we have to talk about the objective function. The objective function J depends on the vector phi, of course. That's the vector that comprises all decision variables of the current time step, but also of all other time steps within the horizon. These decision variables are, for example, continuous and logical control inputs, but also the auxiliary variables that they have to be defined at every time step. Then J also depends on some matrices and the scalar value. The matrix P1 is a constant one, P2 as well as the scalar value P3 both depend on UC and UL. These are the continuous and logical control inputs that were applied in the previous time step. And they also depend on YC reference, a vector that comprises all output references within the prediction horizon. Without going into too much details about how these matrices and the scalar value are constructed, the final optimization problem can be shortly written like that. So we have to minimize J subject to a series of inequalities, and as already mentioned, above all those inequalities incorporate model dynamics, but also some other restrictions, for example input constraints. Solving this by a mixed integer solver, we receive the optimal solution, phi indicated by a superscript asterisk. And we can extract UC and UL, the optimal input sequences, from this optimal solution vector. Then we apply the first elements of these input sequences, UC and UL, at the current time step. And in fact, these are values for the compressor speed, the fan switch, and the compressor switch. So now we have finished one time step, and with this short preview of how we can handle the hybrid model predictive control scheme mathematically, I would like to finish my presentation. I hope I was able to give you a good overview of what this project is about and how we will face upcoming challenges. If you are interested whether in this very topic or in, for example, working together with us on a project of yours, please feel free to contact us. You can find our contact details either on this slide or on our website.